So on this slide, I'd like to discuss with you spectral analysis of projection map. And here's the brief reminder for you what the projection map is. So in order to present a projection map, you need two vectors, A and B. And then when you drop a perpendicular from the tip of the vector A onto vector B, you end up with the vector which we call the projection vector. Here it is. Let me just move this away for now. Which we call the projection vector. This transformation of this map, which assigns projection vector to every vector A, it's a map. And in fact, we proved with you that this is a linear map. And we also have the direct formula for this map. Here it is. T of A, which is a projection of A onto B. Here's a formula, which you discovered in the first semester. Dot product A and B by the length of B vector square times the vector B. Here's the formula for the projection map. You should know. Well, one thing I'd like to comment from the beginning is that projection map only makes sense when the B vector is non-zero vector. Otherwise, it doesn't make sense in terms of geometrical construction, because such a vector will not have a direction. And it also doesn't make sense in terms of this formula. The other thing I'd like to make, another comment I'd like to make is that the projection map, the only non-trivial examples of projection map, they start from dimension 2. In dimension 1, where n is 1, there isn't much sense of considering projection map. Anyway, I'd like to do the spectral analysis of this projection map, and first I will do it on an example. That will give me two opportunities. First, I will demonstrate the properties which are specifically attached to the spectral analysis of the projection maps. And the second, just give me another opportunity to show you how to do the spectral analysis. So what I would like to do is this. I'll take the dimension 3, and I'll take the vector B, which we met already with you, this vector 1, 0, 2. For such a vector, we have computed the metrics of the projection map some time ago. When I will upload my slides on the website, I'll put the proper references to these earlier discussions. Right now, you have to believe me that we have done so. And the metrics of this map, this particular choice of a map, three-dimensional with such a B, if I call this matrix A, the matrix A we have discovered with you, it was like this: 1/5, 1, 0, 2, 0, 0, 0, 2, 2, 0, 4. Like I said, this is just, you have to trust me at this point. When I make the upload, I will make the proper references. Well, I can do it even now. Here we go. If you go to the website, the best way to go through the index, P, projection map. Here's a projection map, example of a matrix. I think that's the one. Here we go. Yeah, that's the projection map. That's the example n equals 3, vector like this, and here's the matrix, you see? So I'm not lying to you. We've done this. Here's a reference for you. Now, if you go back to my slide, close this. This is a matrix, of course, with respect to the standard basis. Now, what I would like to do now is to spectrally analyze this particular matrix. When we do that, the method we were going to follow, it's a method we discussed with you 2 days ago. It doesn't have any particular attachments to the fact that this is a projection map matrix. But later on, when we finish our analysis, we will see some interesting connections or interesting observations. So let's just do the analysis first. First, I build a characteristic polynomial, PA of lambda, which we all know now. It's a determinant of the matrix like this. If I compute such a matrix for this A, here's the matrix. It will be 1 on 5. I'm going to keep this 1 on 5 in front all the time. So when I subtract lambda from diagonal entries, in fact, I will subtract 5 of lambdas, because 1 on 5 is kept in front all the time. So it won't take 5 lambda. The rest of the entries in the first row are the same. 0, negative 5 lambda, 0, 5, 0, negative 5, 2, 0, 4, take 5 lambda. Here's my matrix. I need to compute the determinant of this matrix, and in fact, it is convenient, and I suggest you do it all the time. All the time you're facing a matrix like this, it is convenient to introduce a new unknown, say mu, which is 5 lambda. because that will just let me avoid dealing with the powers of number 5 too much. So if I just introduce this substitution, then my matrix will take this form. 1 take mu 0 2, 0 negative mu 0, 2 0 4 take mu. And now for this matrix I will compute the determinant. Such a determinant it's relatively easy computation because, for instance, second column, it has 2 zeros and only 1 non-zero element. So if I drag my cross like this, I do it the 4th time already. Just still excited about that, right? If I put my cross like this, then the determinant, which is the characteristic polynomial, will be this 1 on 5. What happens to 1 on 5? Normally when we scale a matrix, determinant is scaled by the power of that coefficient, and the power is equal to the dimension. So actually it will be 1 on 5 cubed. Now inside it will be negative mu for this piece, and now the minor, it's this two-dimensional minor like this, right? We multiply this 1 take mu with the 4 take mu. Here it is. 1 take mu times 4 take mu. This one with this, and then the opposite diagonal negative 4. It's this 2 and this 2. If you finish the arithmetic, you will see that here's my front. It is a coefficient in front. 5 cubed is 125. Inside the brackets, if you expand everything, it will be mu square with plus. Take 5 mu, and this is it. Because here you got 4, which cancelled by this 4. This is my characteristic polynomial. Even though it's a cubic polynomial, factorizing such a polynomial, it's a piece of cake, right? So if I ask the question when my characteristic polynomial vanishes, we will see immediately that it will vanish when mu is 0, or mu is 5, or if I project back into the lambda terms, it will be lambda 0 or lambda 1. So here's my eigenvalues. One of them is the eigenvalue 0, the other one is the eigenvalue 1.